Good morning, everyone. Welcome to our second lecture. It's great that so many people still are coming. So, last time we introduced matrix models. Let me just briefly remind what it is. So that's a system defined by an integral. The simplest case that we discussed was the case of Hermitian matrices, dm, the space of n by n Hermitian matrices. With the measure, which is some e to the minus some action, depending on the matrix. So we studied the case when we have this action is 1 over 2 g string trace m squared plus some p equals 3 to infinity 1 over p. There was so the coupling Tp trace m to the power p. And then we looked at perturbation theory. So this is a Gaussian part plus some potential. If we assume that the couplings are small, we can look at perturbative expansion. And then the z is a function of all these couplings and has some non-trivial perturbative expansion in terms of nice Feynman graphs. So we learned about how one can write the propagator as a double line. And then the graphs can be classified according to their topology, and in the large n limit that we studied last time, we get some kind of genus expansion. Similar to what we get in string theory or in ADS-CFT, and we looked at combinatorics and how the graphs get classified by powers of n and so on. So that was our initial thing that we could do with this section immediately. So today we're going to look at more powerful methods, that perturbation theory, and we're going to see how one can reduce this integral from an integral over the space of full matrices to the integral over their eigenvalues, which clearly is possible here because that's defined. So for a matrix M, we can, if we have an Hermitian matrix, we can of course diagonalize it by a unitary transformation. So we write M goes to U dagger. We can write any Hermitian matrix as a conjugation of a diagonal matrix, U dagger D U, where U is D is a diagonal matrix with eigenvalues lambda 1 to lambda m, and U is a unitary matrix. So this potential here is chosen in such a way that the action is invariant under this conjugation, because every trace of m to the n, you can take out this U dagger and U, because, well, U dagger is U inverse. Under the trace, you can combine them, they will disappear. So trace m to the power n depends only on D. Trace D to the power n. So this S actually depends not on m itself, but only on its eigenvalues. And so this integral can be reduced from n by n variables. So we discussed last time that, so Hermitian matrices, the space of them has real dimension n squared dimension. In terms of eigenvalues, it gets reduced to n eigenvalues, which is, of course, a huge reduction, and it makes many structures very transparent. Right, but we cannot just take this integral dm and say, okay, now instead of dm, we just write integral over the eigenvalues and we are done. So that's not a legal operation. So the way such things work is that when this is a linear change of variables from m variables to d, So when we do it, there will be some kind of Jacobian that appears. So this procedure actually is quite similar to what happens in gauge theory when we discuss gauge fixing. So this changing m by conjugation is a transformation under which the integral is invariant. So m going to u dagger mu is a symmetry of this action, which is sort of analogous to gauge symmetry in Young-Mills theory. So if we had a gauge theory, then we would have, and then was a Young-Mills field, then we would have this transformation with also some terms depending on derivatives and so on that we don't have here because it's we don't have any space-time here. So in gauge theory, when we fix the gauge, then what happens is that we acquire some extra terms coming from the Jacobian that can be understood as, that are known as Faddeev-Popov ghosts. So here one can also, so the determinant, the Jacobian that we will find is an exact analog of that. And there are so different ways to derive it. So I will show one of them here. So it's a bit technical. So let me first state what the result is actually going to be. So we will find that Z is up to some coefficient, which is more or less the volume of the unitary group. So this the volume of the unitary group appears because now, so we had integration over M. Now we're going to integrate over D and over U. So U, they represent the compact unitary group, so basically just rotation. So we integrate over D and over these rotations. So what the integration over rotations decouples from all the rest because S does not depend on U. So, it will just give some factor, well, depending on M. So that's will be integration over the unitary group, so volume of the unitary group. This factor is not super important. And what remains will be, so the integral product I equals 1 to n d lambda I. The determinant, the Jacobian determinant that I will write here in a second. So the best way, yeah, let's say delta squared of lambda I. Just a sec to make sure this notation is fine. Well, okay, better to write it differently. So this is one thing. So then product I less than j. Let's write it explicitly. So it will be this lambda I minus lambda j squared. So times the e to the minus s evaluated on the diagonal matrix. So minus s of lambda. So for example, if this s is this trace m squared, so trace m squared would be lambda 1 squared plus lambda 2 squared and so on plus lambda n squared. So we just evaluate this. So all traces will be just sums of powers of eigenvalues. So that's what we will have here in the action. So this piece, this thing, so this is, oops, this is the Jacobian that we will derive in a second, so which appears because we do this change of variables from M to the diagonal matrices. It has a very nice form, just a polynomial in the eigenvalues. It's actually known as the van der Monde determinant. I will discuss that in more detail a bit later. So this is a pretty simple result. Yes. Yeah, but so here the product is over I less than j. Yeah, well, yeah, this weight vanishes for identical eigenvalues, but this is just a set of measure zero in the integration, if you want. So this it does not really contribute. Well, you can think of an example, let's say like dx, integral dx dy, e to the minus x squared minus y squared, and then this thing would be like x minus y squared. But it's not a zero integral. If you can expand this, okay, it will be x squared plus y squared minus 2xy. So this guy will not contribute because of parity, but these guys will, and it will be something quite non-trivial in principle. So, well, I mean, the fact that the integrand vanishes somewhere, just on some subspace, it doesn't mean that the result is in. So this thing also is positive definite, so it's all nice. And everything is still, remember, this S has a Gaussian term, so everything is still, which will be minus the sum of squares of eigenvalues. So everything still is at infinity suppressed exponentially. So any polynomial insertions like this are completely fine, and the integral is well defined, it's regular and so on. Right. Any more questions? Okay. Yeah, so there are different ways to derive it. So one can do some tricks with delta functions like we do in the field theory often when we derive Faddeev-Popov things. So in the literature, you can find different derivations. So this, I will give another one which is more explicit. So this is quite a technical piece of calculation. And I mean, it's not extremely important, all the details. I will give them so that you can get a flavor of how it works. But maybe I will skip some super technical things here that you can find in the literature later. Anyway, what's important is the result, and we will look at its properties. So, but let's try to actually derive it. So we will do the following. Instead of directly computing this Jacobian, so one nice trick is let's look at so what we can, let's consider a small variation of our matrix and look at the norm squared of this variation. So such an object, so if we had just a variables like x, y, and so on in the integral, so this would be like delta x squared plus delta y squared, and so on. So you can say it's basically the metric. The metric in our integration variables. So what we will do is we will compute how it changes, what it becomes in the new coordinates. And then, so we will find the metric in the new coordinates. What we actually need for the integral is not the metric, but the volume form, which can be read off from the metric. So basically, the volume is the determinant of the metric, roughly speaking. So that's how we will derive this thing. So let's see how it works. So delta m squared. So the actual, well, to write it, we say it's just the sum over all ij, absolute value of delta mij squared, which can also be written as trace of delta m squared. So we take the matrix delta m, take its square, and take the trace. So now let's write it in these terms. So what is delta m? So delta m will be delta u dagger, delta of u dagger, du plus u dagger delta d u plus one more guy, delta u dagger d delta u. So this delta of u dagger can be simplified in terms of delta u because we know that delta of u dagger u is 0. U dagger u is just identity since it's a unitary matrix. So this first piece we can write as, well, delta U dagger is so minus U dagger delta U dagger. Let's okay, let's write it a bit more carefully. So we say delta of U dagger times U plus U dagger delta U is 0. Writing out this equation. So then, so then if I move this to the right hand side and multiply from the right by U dagger, I will get exactly this. Okay. So we get these three terms. So now let's write them here. Trace of so this one I plug in. So minus U dagger delta U dagger du plus, so from this one, U dagger delta du. Actually, sorry, let me reorder them to put this one to be the second one because it contains delta U just like that. So this will be U dagger d delta U. And then this one, so U dagger delta du. So trace of this thing squared. Right, so now it's a bit, so any questions for now? Yeah. So D is a diagonal matrix, yes. Delta D is also diagonal, yes, exactly. The first, the which one? So this and, wait a second. So first of all, diagonal matrix is not the same as scalar. Because if the entries are different, it does not commute with other matrices. So that's an important thing, right? So if generically, of course, all lambdas are different. So you cannot just commute it with U or anything else. So it's not as simple as it may look. Any more questions here? Okay. So yeah, so we have the square of sum of three terms. Okay, so now it's a bit painful to like open the brackets and collect all terms. Also noting that we can use the trace to move things around. So for example, let's look at the term with delta D. So there is a term when I square this. So trace of this thing squared. Trace of U dagger delta D U squared. So that's trace of, just let me write it super quickly. U dagger. U dagger delta D U dagger delta D U. But this U dagger is 1. And also I can move U dagger here through the trace. That will combine with this U and they also give 1. So it will be just trace of delta D squared. So although it looks quite horrible, actually when we start simplifying, the result simplifies quite a lot. So we already have spent quite a lot of time on this. So let me skip maybe a couple of steps and leave that to you as an exercise. I will write the result of this simplification and explain where it comes from. So this thing star. So we will find that it gives the following. So it's useful to introduce some notation for this delta U. So delta U itself is not a real quantity. U is a unitary matrix, so variation of a unitary matrix is something complex. But what is real is delta, let's write small delta U, defined as 1 over I delta U, U dagger. So this matrix you can check is Hermitian. Small u, distinguished from the large one by absence of this thing. So this is an Hermitian matrix for the group U1. This would literally be the angle e to the I phi, this angle phi. But so it's trivially related to delta U that we have here just by this extra U dagger. So in terms of this, we will find this becomes the following. So the square of this term we already computed, so that trace delta D squared. So next, the terms with delta U times delta D. So when we open the brackets, there will be a cross term when we multiply this by that. So that can be done in two orders. So, this by that and also this by that. So, and also one should remember that these are non-commuting objects. So, for example, we can multiply this by that, plus there will be a term when this comes first and that comes second. So if we keep track of all this carefully, this cross term becomes the following: plus 2i trace delta U small, commutator of delta D and D. And then the most complicated is the term when delta U is squared. So when we multiply this by itself, or this by itself, or we multiply one by the other. So that one will give 2 trace of minus delta U D, delta U D, plus delta U squared D squared. So an exercise is to derive this starting from this trace of the sum squared. So again, why we introduce this delta U? To keep everything in real variables. So this delta U is some parameterization of the unitary group in a real term. So what can we say here? Any questions at this point? Right, so this thing, so it's a trace of delta U times commutator. But like I just mentioned, so following a question, so this delta D is a diagonal matrix. D is also a diagonal matrix. So we have here a commutator of two diagonal matrices. So that means it is 0. So this guy does not contribute. So already we find nicely that here delta D and delta U do not mix in this metric. So, and then the second step is if we write this explicitly in components, which I will also skip here and leave to you. So we will find that, so the first term is like it was. So we can rewrite it already in eigenvalues. So this delta D squared is just the sum of I equals 1 to n delta lambda I squared. And now this one, if we write it in terms of eigenvalues, this will be the following: sum over ij from 1 to n delta u ij delta uji lambda I minus lambda j squared. Well, it's kind of believable that this structure can be true because, so here we have D, D, and here also D. So D appears quadratically, and there are some minus signs here as well. So if we write it in indices and shuffle a bit the terms around, so we will find this structure. So that I also don't want to spend too much time on, so I leave that as another useful exercise. So at this point, we are almost done. Because, so we have what we have found is the metric in the new coordinate. So in general, if we have a metric, delta L squared, let's say it looks like GAB, delta LA, delta LB. So then to compute the volume form, the thing which appears in the integral. So this will be, well, like DL, volume. So this will be a product of all DLA times the square root of determinant of this metric, or of this metric, determinant AB, GAB. And that's like a standard formula from differential geometry, which probably you have seen. Sometimes, like for example, when we do the Polyakov action, this kind of thing appears as an induced volume form on the worldsheet. And anyway, that's a pretty standard formula. So now so here we computed this metric. Now we just need to read off this metric. So now that I was thinking about on the tube, and it was a bit too much for me to do it abstractly. So let's consider the case n equals 3 and deduce what happens from there. So let's say n equals 3. We need to compute the determinant of these coefficients. So first of all, which coefficients do we have? So we have this delta U11, delta U12, delta U13, and so on up to delta U33. They are all just some real variations. So what we can see immediately is that the diagonal, if I is equal to j, then this coefficient vanishes, so the diagonal ones are not present in this expression. Delta U11 is not present, 33 not present. So the only ones which are left are the off-diagonal ones. Well, and also this is clearly symmetric in I and j. So it's enough to look only at delta U12, 13, and 23. So, so we have basically these three variables and the metric in these three variables. So if we write them like this, so I can write the metric as a 3 by 3 matrix. So with these labeling the columns and the same for the row. Also notice that they still don't couple to themselves. So delta U12 couples to delta U21 because of these indices. Well, that's a bit sloppy notation from me. So it's actually, yeah, so there will be three of them, but better to write it in a slightly different way. So let's look at the piece where delta U12 couples to delta U21. So this 2 by 2 part of our big matrix, so the diagonal ones entries are 0. The off-diagonal ones will be this lambda 1 minus lambda 2 squared. So lambda 1 minus lambda 2 squared. So that if all we had was this, so if n were equal to 2, then this would be just the square root of the determinant. Would just be this lambda 1 minus lambda 2 squared. So like I said, so this will be, so we find exactly this factor. Right, but then if we have larger, so for n equals 3, so one should still be able to do it quite explicitly and write down this matrix. And so then after assembling all the pieces, we will find that they boil down to this determinant again. So to this product. Let me actually not do this because I think everyone is getting bored with this calculation already. So just to reiterate, so we have this thing. From this, we read off the matrix, which couples the variables. And we compute its determinant, and like after some tricks, which are pretty simple here, we find this factor. Okay, so I skipped a couple of steps, but I hope the logic of what's going on is clear here. So just to recap, so we started with the action depending on traces of m to the n. So we observed that this action has this symmetry. So then we split, what we want to do is to diagonalize the matrix. So we do kind of gauge fixing when we say our matrix is diagonal up to a unitary transformation. So then we find the Jacobian in these new variables. So it will be that. So one thing that remains to be said, again a bit technical, is the following. So, but conceptually it's quite important. So we had integration over m. Now we will have integration over this. So from m we integrate instead now over u and d. So the integration over d remains here. It's the integral over eigenvalues. So integral dm, integral over d u, and integral over d d. So this is what we have here. But this integral over du, it will be the integral over these delta u variables. And this will be the basically the volume of the un group. Now this measure, so these variables delta u, they define what's known the HR measure on this group. So what one subtlety here is the following, that if we take u itself to be diagonal, so then it does not introduce any new variables, so because it will commute with d. So in other words, if we have some u satisfying this property, we can always multiply it by a diagonal unitary matrix, and it will still be true. So to avoid overcounting, we have to say that we do not take into account these matrices, because we would like for this decomposition sort of to be unique. So to be one-to-one map between m and the space of u and d. So since the choice of u is not unique, we have to quotient by this in the integral. So roughly speaking, we find this integral over un matrices divided by the diagonal matrices, which are u1 to the n. So this coefficient in front will be this integral. So it will be some quite non-trivial integral in the delta u variables. But we don't care about it because it, in any case, does not depend on lambdas in any way. It's just integral over delta u. So there are ways to compute it, and actually using some tricks, maybe we can discuss in the last lecture how it can be found explicitly. It's actually a quite an explicitly known number given by some gamma functions or factorials and stuff like that. Okay, so that was quite somewhat a sketch of a derivation, but I hope what's going on is more or less clear. So basically, that's the integral of the gauge group, and that's the gauge fixed model. Any questions? So let me now just briefly describe what is this guy that we found here, because it will be really important in what follows. Yeah. Yes. Well, because like every entry is a phase. So we have n phases, so it's u1 to the n. Well, since I didn't really explain how to compute this integral, it's just hand-waving notation, but that's the idea. Yeah, so this thing, so it's normally called delta of lambda, product of over I less than j, lambda I minus lambda j. And what we have here, this is delta squared. And by lambda, I mean the set of all lambda. So this is known as the van der Monde determinant. Why do I say it's a determinant? Well, because one can actually show that it's the determinant of the following matrix. Determinant of the n by n matrix, where we determine written as lambda I to the power j minus 1 over ij going from 1 to n. So this notation may look a bit fishy. It's just to write it explicitly. It's the matrix where the first, let's say, column is built out of ones, 1, 1, 1. The next column is lambda 1, lambda 2, lambda 3, and so on. And the next is lambda 1 squared, lambda 2 squared, lambda 3 squared, and so on. So this determinant, maybe in your linear algebra course you have seen it. Some advanced textbooks have. This is a kind of exercise to show that this determinant is actually equal to that product. So how do we see that they are the same? There are many ways and tricks to it. The simplest one is the following: to observe that we want to prove that this is equal to the determinant. So observe that both of them are polynomials in lambda. So let's look at the degrees of these polynomials. So let's pick one variable. Let's say lambda 1. So then you can see here the degree will be degree with respect, let's say, to lambda 1. So it will be n minus 1 over 2. Here, because that's the number of factors with fixed, so where lambda 1 appears. And the same is true here. Yes. And so they have the same degree. So actually, wait, I think I'm seeing some stupid thing. 1 second. No, wait, sorry, that was stupid. The degree is not that, it's just n minus 1. So if we single out, let's say I equals to 1, okay? Then there are n minus 1 terms with lambda 1 there. And here also the degree of this polynomial will be the same number, because the highest possible power here would be n minus 1. And if we pick that power, then we cannot pick lambda 1 from any other place in the matrix. if we say pick the element from the last row, then the contribution to the determinant will be that element times the minor that does not include lambda 1. Since if we pick this element, then we have to pick all the rest from this submatrix. So the degree in every variable of this polynomial is n minus 1. Well, and so the last thing to note, this determinant vanishes if two lambdas are identical, because two columns will become, so two rows will become the same. And the same is true for that expression. So we have two polynomials that have the same degree and the same zero. So that basically means they have to be identical. So this is a sketch of a proof of why this delta of lambda is equal to the determinant. Well, and it's quite natural that it is a determinant because we derived it as the Jacobian determinant. So this is the trick when rewriting this product as a determinant is useful for various applications that we will probably also discuss in the last lecture, and that connects the whole story to the theory of orthogonal polynomials. So now I think is a good time for a break. Any questions before that? After the break, we will look in more detail at how to compute this integral in various ways. Okay, let's do the break now. Okay, let's restart. So let's continue. Right, so what happened is the following. So we had an integral over the space of all matrices. So we split them into diagonal part with eigenvalues and the unitary matrix. So then we managed to do the integral over the unitary matrices, and what's left is the integral over diagonal matrices, so over the eigenvalues. So let me write it down once again. So we have the integral over dm is equal, roughly speaking, integral over the unitary matrices times integral over the diagonal one. So this one gives something like volume of un. Whereas this one is what we want to compute. So we can write more concretely also what kind of observables we can study. So what we will study are expectation values of some f of m, where f of m is a gauge invariant quantity. So like, for example, f of m equals trace m to the n, a trace m cubed, or trace m squared, and so on. These are the typical observables that are easily accessible in this framework. So because when we do this change of variables, they will not depend on u. They will depend only on eigenvalues of the matrix. And so if I compute the expectation value of, say, trace m cubed, here I will just get the trace d cubed, which is the sum of all lambdas cubed. So I can say expectation value of f of m. So it's 1 over, so it's the integral with this insertion divided by the integral without any insertion. So I can write it like that. Well, okay, let's not. Yeah, so first to emphasize that this f of m, it will be the integral of Cn integral d lambda f of lambda. So this delta squared of lambda e to the minus s of lambda divided by Cn, the same thing without f, delta squared of lambda e to the minus s. So and you see that in such observables, this Cn, the volume of unitary group, will cancel. That's why we don't really care about it. So we need to learn how to compute integrals of d lambda with this delta squared, e minus s, and some function f of lambda. So concretely, notice that actually, if I take something like trace m cubed, so we will have this integral d lambda. D lambda is just the product of all delta d lambda I, delta squared of lambda e to the minus s of lambda. So times, so this would give that times something like lambda 1 cubed plus lambda 2 cubed plus 1 plus lambda n cubed for this case, trace m cubed. But everything in this integral is a symmetric function of lambdas. So this thing I can remove, I can replace by n lambda 1 cubed. So integral dn f of m e to the minus s will be integral d lambda n f of lambda 1, let's say, e to the minus, so delta squared of lambda, e to the minus s of lambda. So we can combine this Jacobian and e to the minus s together and call the result the effective action. In the m variable, we just had s of m, but now it also comes multiplied with this thing. So how to write it explicitly? So remember, so our s started with Gaussian term plus potential. So now if I bring this into the exponent by just saying that, okay, it's exponent of 2 log of delta, this S effective will be the following. So 1, first the Gaussian term, 1 over 2gs sum I equals 1 to n lambda I squared. This is just trace m squared that we had originally. So so since it's minus here, but this is to the positive power, will be here minus 2 sum over I less than j log lambda I minus lambda j. This is just the logarithm of this guy, the logarithm because I brought it into the exponent, and that coefficient 2 is because it was squared here. Well, and then the non-trivial part of the action was the potential, the original V of n, so which will be here sum over n, well, what I call the sum over p greater or equal to 3. And we have trace m to the p, which is sum over I equals 1 to n. So the coefficient was Tp over 2pgs, so gs was in front of everything, and lambda I to the n. So this is our potential V of n. So remember, gs is here only for pedagogical purposes. Well, actually, you can set gs equal 1 over n. Okay, any question? That is, oh yes, great, thanks. Lambda I to the p. Right, so I just reabsorb this prefactor into the exponent and call the result the exponent of the effective action. So now we're going to see how to study effectively the large n limit. So n goes to infinity. So last time we discussed how it looks in diagrams. Here we will study it analytically. We are going to invoke a saddle point kind of argument. So we will argue that this action, this effective action, is actually large. So since this is just e to the minus s effective of lambda, if this thing is large in n, then the whole integral will be dominated by the saddle point of this expression. So in other words, by the solutions to equation delta s by delta lambda equal to 0, which are kind of the equations of motion. Here, it's just a finite dimensional integral, of course, but so when you have an integral of minus something large in the exponent, then you have to look at points, at stationary points of this function. They will give the leading contribution to the integral. So in fact, this S effective is of order n. Let me just make sure. Yes, n. So just to be sure, no, not n, it's n squared. So why? So we will see. So let's justify this later, but for the moment, let's just assume that lambdas at large n scale as 1, the relevant. So the dominant parts of this integral will be when lambdas scale is 1. So then the first term here, for example. So this is a sum of n terms, each of which is of order 1. And also it's multiplied by g string, so divided by gs. Gs is 1 over n itself. So it's n from gs times n from the sum. It scales as n squared. Now the second one, this is a sum of n and minus 1 over 2 terms, each of which is of order 1 itself. So again, it scales as n squared. So and let's okay, and then the last one will also in the end have a similar scaling, but let's for the moment assume, just for simplicity, that this potential is not present here. So let's just say v equal to 0 for now. Well, actually, okay, we can see immediately it also has the same scaling because 1 over, for the same reason as the first one. This 1 over gs is order n. Here, sum of lambdas, sum of n quantities. So they all scale in the same way. But still, so let's for now assume that v equal to 0. And in the next lecture, we will see what happens when v is actually non-zero. So let's, for the moment, focus on the large n limit for the Gaussian matrix model without any potential, which is already quite interesting. So what we will derive is the famous Wigner's semicircle distribution for the eigenvalues. So let me write, so the last equation I will write including v is, so the condition of a stationary stationary function in the exponent. So like I said, we have an integral where the expression in the exponent is exponentially large in our parameter n. So it's exponent of minus n squared times something. So the dominant contribution to the integral will come from the place where this function is stationary. So we write what you can call equations of motion. Which is delta s effective over delta lambda I equal to 0. So n equations. So, okay, so this first term is quite easy to write the variation. This will be, so just a second, I think there's some sign problem. Well, so it's convenient to, the thing is 0, so let's choose the sign such a way that this comes with minus. So it will be minus 1. If you want, I can write minus here, just for later convenience. So this will be minus lambda I over gs. Then derivative of the log, it will be 1 over this thing. Yeah, so sum j not equal to I, 2 over lambda I minus lambda j. So then minus v prime of lambda I equal to 0. So these are the saddle point equation. So this guy, for the moment, we assume is 0. So let's look just at the first two terms. So notice the scaling is fine. So this first term is 1 over n, is n, order n, because G string is 1 over n. And this is a sum of n terms, so it's also of order n. So they combine nicely. So this is a set of n equations, just algebraic equations, simply rational functions of lambdas for n variables lambda I. So they have some nice discrete set of solutions. To people familiar with integrability, they may remind a bit the beta-ansatz equations, which are pretty similar to what we have here. So, but remember, the number of variables is actually large. So how can we try and solve this equation? Yes? Well, this, so I less than j, because here from the beginning we had this delta squared, which it was literally delta squared was I less than j, right? Lambda I minus lambda j squared. Ah, yeah, maybe that's the reason why the 2 was not here. Oh, yes. If I write it, yeah, it's good. Yeah, great, thank you. So in this notation, there will not be any 2. Because here I wrote j not equal to I, so then the terms get combined, which would differ by permutation of I and j. Like, for example, if we had, so if I had like n equals 3, that would be lambda 1 minus lambda 2, lambda 1 minus lambda 3, lambda 2 minus lambda 3. That what, so does it actually? So that's what I would have here. No, wait, I think it's still a mistake. It should be actually 2 here, even because of that. Yeah, so, well, the reason is here it was a double sum. It was sum over I and over j. Now I'm differentiating in one variable, so I need to look at only places where lambda I itself appears. So this thing is basically lambda 1 let's say I equals to 1. So it will be lambda 1 minus all the other lambdas. So I will have a sum over lambda 1 minus all other lambdas. So it will be like that. And I think the factor of 2 actually needs to be here. No, actually. So you can check that by looking explicitly at a couple of cases. But because this thing was originally symmetric in the I and j, because, well, it was to some power squared, then it will be fine. Because if they are exchanged, then the other one it will be like 1 over minus the expression, but also another minus will come from differentiate. When you differentiate, will be a minus sign. Well, I mean, so the best way to derive it is just look at the case like n equal to 3. Then there are 3 brackets. So let's differentiate in lambda 1. So they were all squared. Differentiate in lambda 1, it will be 1 over this and 1 over that. So it will be just like written here, lambda 1 minus 2 and lambda 1 minus 3. And then when you, so that's how it will be for lambda 1. But this thing is symmetric in lambda, so for other lambdas it will be the same structure. Your lambda minus all other lambda. And the coefficient has to be 2, I think. Okay, these were great questions. Any more questions? No. Let's not go there. Well, you can no. Well, I mean, we all know complex numbers, so it actually. But well, if you want, you can put an absolute value; it will still be true. But I mean, even without absolute value, it should be fine. But there is no such thing here because it's sum over I less than j. Well, yeah. So this, what I'm saying, this double sum translates into this one. So the argument, let's say again, we have n equals 3. So we have these 3 brackets. Okay, they go to the exponent, they become logs. But let's say we are looking at lambda 1, then only these 2 ones are relevant for that, right? And then they give 1 over this and 1 over that with this sign just as written here. So our lambda minus other lambda. So that's for lambda 1, but if we look at another lambda, we can rewrite these brackets in by exchanging the order. And the expression will still be the same because it's this thing is symmetric in all lambdas. So, well, I hope you believe this argument. If you don't just take literally this n equals 3 and compute the derivative. So we are differentiating a function which is symmetric in lambda, so the derivative will have to have this universal structure without anything like extra signs when we switch them and other garbage. It could potentially appear in other cases, but not here. Okay, so any more questions? Hope that was convincing. You know? But, so this too worried me a bit, but I think it should be true. Okay. Should you think it should be 1? Well, so we start from this, let's say, okay? Just so product of different pairs. And each pair comes with a square. So when I bring it to exponent, it will give me 2. And then if I say I have lambda, I have I equal to 1, it will be a sum of, well, 2 terms on this and that. So this and that, and I don't see why anything else should be different. Well, yeah, you can say so, yeah. Yes, that's another way. So do you agree that it's 2? Yeah, okay. Yes, that's right, yeah. Yeah, you can say here, for example, let's say, okay, it's minus sum over I not equal to j without 2. Like someone was mentioning, it could be easier to understand. Then we just differentiate it, and just then we get this sum over I not equal to j. But then there will be double, each term will actually appear twice, so we will give also. Okay, so we have like 3 ways to derive this equation now. Hopefully it's correct. Okay. So let's see how we can solve this system of equations when n is large. So first let's try to understand what actually happens here. So this thing, this log is actually the electrostatic potential in 2 dimensions. Well, we can think of lambdas as complex. In some cases, the saddle point will actually be complex. So these are, we can think of them as points on the plane. So being repelled, so sitting in this electrostatic potential. And so what we have here is kind of like the force, which consists of 2 parts. So this first is the overall potential, linear in lambda, so that corresponds to a quadratic well. This S effective. Well, you can see here the quadratic term. But then this thing is an interaction between particles. So each lambda I kind of sits in this potential, and the overall force acting on it has to be 0. So the first piece of the force is this one coming with a minus sign, because if I have, let's say, lambda I here, so there will be a force acting in the opposite direction, which is this minus lambda I over gs. So we're bringing it to the center. But then the second one will correspond to, the only question is repulsion or attraction between them, and actually it is repulsion. To find this out, we look at the sign. So if I have another, let's say lambda j sitting here, so then this thing will be 1 over lambda I minus lambda j. For this configuration will be positive. If lambda j is smaller. So this will give a positive force, which means it goes to the right. 2 over lambda I minus lambda j. So to the right, so that is farther away from this other particle. So that means it is repelled by the other particle, but at the same time attracted to the center of the potential. So we have a set of equations for equilibrium of these n particles which sit in the squared potential, but also repel from each other. If there was no repulsion, then they would just all sit at the bottom of the well. Well, obviously, if there was no such term, then lambdas would just all be zero. But because of this, if they want to come to the center of the well, then they start repelling each other. And actually, they feel some kind of configuration here, which in principle is non-trivial. So the way, since there are lots of them, we can, in the end, one can see, say, numerically by solving these equations, that they will occupy, so on lambda line, there will be some region to which they condense. So they will densely fill some segment of the line, or in more complicated cases, several segments of the line or of the complex plane, to where all lambdas will sit. And they will fill it with some density. So we can, not necessarily uniformly, so we can, so for example, if we plot what happens, let's say n equal 4, we have 4 particles, so n equal 8, n equal 10, we start to see more of them, and we observe that the solutions to these equations, they behave in such a way that lambdas stay of order 1, and they are restricted to a given fixed interval. So when n becomes large, they fill this interval completely, like in a dense way. So just like I drew here. So they will fill it with some density that we can call rho of lambda. Well, we can define it, if you want, by sum of delta function. Sum of I equals 1 to n, delta of lambda minus lambda I. But which will, for large n, condense to n, because it's of order n, times some something of lambda, times some non-trivial function of lambda. And our goal is to try and find this function from those equations. Well, if you want, another way to introduce this density is the number of particles between whose lambdas are between lambda, so number of particles in whose lambda is from lambda to lambda plus delta lambda, divided by delta lambda, such that the integral of this rho is the total number of particles n. So we look at the solution of this equation for many particles, and we look at some small region of the lambda line of size delta lambda centered around the value lambda. there will be some number of solutions sitting inside this region. So, and this quantity will define the density of solution. Well, it's a pretty standard kind of object that we use when we have equations with this distribution of roots. And for orthogonal polynomials, for example, similar things can be defined. In the what picture? Sorry.
Yeah, that
Yeah.
So the further actually from the center of the potential.
Yeah.
So the further it will be repelled outside, right?
Well, not necessarily. I mean, so
all the lambda, like most of lambda will be inside near the potential, and the repulsion force will be greater than the for finite.
Wait. So if it's far away from the others, then the repulsion force will be small because it's 1 over lambda. The repulsion force is this fraction, right? It's 1 over lambda. So if you
when you say that this is taking repulsion from left side, but also like lambda on the right side will also.
Yeah, it's not repulsion on the left side. It's literally repulsion between any two of them, regardless of where they are globally. They always get repelled from each other.
Yes, sir.
This is what I meant to illustrate here. That if this guy is from the left, then the force is to the right. But if we did it the opposite way, we would find that it's
yeah. If the lambda is
yeah.
Right.
Yeah, if many are here, but one is far away. Yeah.
Yeah. So there will be many other lambdas. All of the lambda will be on the left side.
Yes.
The repulsion force will be more than the acceleration.
But no, but if lambda is far away from them, then the repulsion force will be very small.
But there will be more number of lambda.
Well, yes, still, but yeah. So, well, this kind of these effects will actually, in the end, cancel each other. But if you, well, if you are really far away from them, then since this thing does not, this thing grows, really, this thing grows depending on the value of lambda, and regardless of how many other lambdas there are. So if you move far away, you can always make it really big. And so in the end, it will get attracted there. Yeah, that's a great question. Nice. Like this kind of logic is what you have to always invoke here. Like that's one explanation for the balance of these terms. So even this repulsion force could be parametrically large in n. If you make lambda really large, you can still make this attraction force even bigger. That's a nice sanity check. Yeah. Oh, yeah, if it's unbounded below, it would be pretty bad. Then, in some sense, the original integral would not converge. So that mainly would correspond to like having, let's say, I don't know, minus x minus m to the 4 potential. So then that's how it would look like. Yeah, because I mean, this perturbative part, in principle, could be well, dominant compared to the Gaussian part. Well, still, you can sometimes do things even there, but. So here the logic is that there is like some energy level and they sit here, roughly speaking. So any more questions? That's important and nice point. Okay, so we introduced this density. So now let's see how, so we at the moment we have equations on lambdas individually. What we would like is to have an equation on the density, because the individual lambdas don't make much sense anymore. So, yeah, so for that, so how to convert this into an equation for the density? So the trick is to introduce what's known as the resolvent, which is integral of the density divided by difference of arguments. Integral d mu rho of mu divided by lambda minus mu. So again, this is an object of order n. And often we could rescale it by n from the beginning, but let's keep it like this. So then, so how, first of all, how can we relate it to the density more explicitly? Well, there is a nice relation that 1 over x minus I epsilon minus 1 over x plus I epsilon is actually a delta function 2 pi I delta of x. So this relation, to see it, you can integrate both sides with a test function. And then, so it's kind of integral of f of x divided by x. Which, because if there was no epsilon, then this integral would kind of be 0 because you are subtracting two identical things. But because of this epsilon and imaginary shift, you can deform the contour a little bit, and you will find that it boils down to residue at 0. It will give you your function at 0, roughly speaking. So that's the kind of logic valid here. So that means that we can, so this thing, g of lambda, you can visualize it as having a cut on the complex plane between the endpoints of this distribution of lambdas. And on this cut, it jumps. So the value by which it jumps is proportional to the density. By virtue of this identity, or if you want to, you can like see it more explicitly by integration. So there is a relation of the kind g of, so here one should be careful with the stupid signs and i's. Just let me see. Well, okay, so here the sign might be off, but hopefully it's not. So g x minus I epsilon minus g of x to lambda minus I epsilon, g of lambda plus I epsilon is 2 pi I rho of lambda on the cut. So these kind of, so on the cut, g jumps by the amount equal to the density, whereas away from it in the complex plane, it's a nice analytic function given by this integral. Well, obviously you can see that if lambda is on the cut, then the function is not really well defined. But actually this integral will give a finite function everywhere, only it will have a jump on the cut by some finite amount. So you can convince yourself that all of this is actually true. If you take the density to be a square root, you can explicitly find this function will also contain just a couple of square roots. We will see it explicitly probably in the next lecture. So and that's how this looks like. Yeah. Okay, so that's that. Yes? Yeah. Yeah, so the density will be restricted to some finite segment only. Yeah, this is an assumption which will be justified by the result. If you, well, of course, it's not a valid logic. So actually, at this point, we have switched a bit from completely rigorous steps that were before. When we discussed large n, this is now, I mean, not super rigorous. And in fact, some mathematicians have built their careers on proving this kind of thing, these statements. Maybe someone even got a Fields Medal or something for them. You know, so that's so here we are back to like the physicist kind of rigor, whereas to make it completely mathematically sound is not that easy. That's a good point, yeah. So yeah, so let's see. So I introduce one of the main. So in fact, I think at this point, I think it's time to stop for today. So we introduced the main objects like g of lambda, rho of lambda to this effective action distribution of eigenvalues. And the next time, let's see how to actually solve these equations and what will be the solution. Thank you.